Lattice energy refers to the energy released when gaseous ions form 1 mole of a solid ionic compound. So for this NaCl example, NaCl is table salt, all right, and this is going to be in the solid form. And lattice energy is just how much energy is released when the Na plus ion in its gas phase plus the Cl minus ion in its gas phase produces this NaCl, right? How much energy does it release when you have these gaseous ions forming your ionic compound? And it turns out that it releases 787 kilojoules per mole. So for every mole of NaCl that's formed, it's going to release this much energy. The reason it's a negative sign right over here is because negative sign refers to the fact that you are releasing energy. So maybe more specifically, I should write releasing. All right, whenever you're releasing energy, it's always going to be a negative sign for your kilojoules part, right? You're going to be releasing energy. Now, the magnitude of this lattice energy also tells us a lot of information about your ionic compound, right? And lattice energy is essentially used to find out how strong an ionic compound is, essentially, right? How strong are those attractions between the individual ions in your ionic compound? For example, let's say if we're trying to find out if NaCl or magnesium oxide, let's say if I want to find out which ionic compound is essentially stronger, right? Magnesium oxide, you might remember that ionic compounds, they have something known as a crystal lattice. So you're going to have your cations, right? And your anions, and it's just going to be this repeating sort of structure, right? This is going to be your crystal lattice. And lattice energy essentially helps us figure out, well, how strong is this attraction, right? What you have to remember is that the greater your lattice energy, the greater the strength of your ionic compound. So in this case, right, notice how NaCl has a lattice energy that's lower than magnesium oxide's lattice energy, right? Magnesium oxide's lattice energy is 3,795 kilojoules of heat that's released, right? And that basically, this bigger number basically just tells me that, well, it's this magnesium oxide ionic compound is going to be essentially stronger than this NaCl compound. If we were to take a look at, let's say, the next two examples, right? We have lithium fluoride and we have calcium oxide. And I want to find out which one of these compounds is essentially stronger, right? Which one of these compounds has the stronger ionic bonds? And, well, it's going to be calcium oxide because it has a higher lattice energy. Okay? Now, what if you weren't given these values? What if you were not given these values? All right, and you wanted to find out which compound is stronger without looking at the table. How would you do this? One thing you have to kind of know is Coulomb's law and how that kind of works, okay? Now, when you have two charges, right? Now, let's say these two charges are attracted to each other, and recall that opposites attract, right? So this positive charge and this negative charge is going to feel a force of attraction to each other, right? It's going to feel some force of attraction. Now, the greater these charges, the greater the magnitude of these charges, well, the greater the force of attraction. For example, let's say if these two particles are 5 feet away from each other. And let's say I drew the same diagram, except these particles, instead of just a positive charge, maybe it's a very big positive charge. So it's a greater positive charge, and this is a greater negative charge, right? But it's still 5 feet away from each other. Well, they're going to feel a greater force of attraction to each other. And therefore, it's going to be like a stronger sort of bond if we're talking about ionic bond, right? The greater the magnitude of the charges, the stronger the bond, and therefore the greater the lattice energy. And the other thing you have to consider is distance. Distance also plays a role in the force of attraction between two particles. If these two particles were pretty far away from each other, okay, they would feel some force of attraction to each other. But if the particles are very close to each other, then they would feel a very strong force of attraction to each other. So the point to know here is that smaller, in this case, smaller sort of ions equals stronger charge. Stronger charge. All right. The smaller the ion is, the stronger the charge is going to be. If let's say I have a very big atom right over here, let's say this is a cation, this is anion. Okay, it's going to feel some force of attraction. right? However, if the atoms are smaller, well, notice how now the centers of our atom, or I shouldn't say atom, I should say ion. Notice how the center of my ion is now closer to each other. And that means that when smaller ions have smaller, basically, radii, right, the nucleus radii, then their centers can get very close to each other. And when the centers are closer, the distance is decreasing. If you look at Coulomb's law, right, notice how distance plays a role in the force of attraction. The greater your distance, right, if your distance is further away, you're going to feel a less force of attraction. In this case, our distance between the two centers is decreasing. That means the force of attraction is increasing, right? This is why distance is in the denominator, because distance plays a very big role. It's an inverse relationship, all right? So as distance increases, force of attraction decreases. As distance decreases, force of attraction increases. Now, let's say if we were to take a look at this other example right over here, magnesium fluoride versus calcium oxide, well, if we take a look at magnesium fluoride, well, clearly you can see that, well, magnesium and fluorine, they're going to have lower charges than this calcium and this oxygen, right? Or this oxide ion, right? So calcium oxide is going to have a higher lattice energy because overall the charges in this compound is going to be greater than the magnitude of the charges in the other compound, right? This is only 1 minus, but then this 2 minus sort of counteracts that, right? It makes the lattice energy go up. Now, if we wanted to compare NaCl and KBr to see which one has the higher lattice energy, well, remember, the first thing we do is check the charges of each ion in each compound. So Na has a +1 charge, Cl 1 minus, K, potassium, it also has a 1 plus charge. Bromine also has a -1 charge. So the charges are the same. So when the charges don't work out, right, they're the same, you're going to see which ionic compound has the smaller atoms, the smaller ions. And the smaller the ion, the higher the lattice energy. Because then the distance of the two things decrease. And now recall that as you go down a group, the atomic radius increases because you're adding more shells to the atom. While if you go left to right, aka across a period in the periodic table, your size is going to decrease because as you go across a period, you're adding more protons, and that's going to pull the electrons closer to the nucleus, so the size is going to decrease. Now, if we take a look at the cations, notice how potassium is below sodium, and we know that as we go down a group, the size is going to increase. So this is going to be bigger than Na, and this is the same case for bromine and chlorine. Bromine is below chlorine, and as we go down a group, atomic size increases, so bromine is also bigger than chlorine. Now, we said how the smaller the ions, the greater the lattice energy. So that means that NaCl will have a higher lattice energy because the atomic radius or atomic radii for these nuclei, that's going to be smaller, right? These